Okay, hello everyone. Welcome back to your YouTube channel and welcome to this very interesting and fantastic video of today. As you must be aware, we have been working with this very brand new module that is called Electromechanical Conversion Systems. And when you are dealing with this kind of devices, one of the very important aspects is the whole performance of this conversion system. So the performance is strongly connected with the main features, the characteristic of the magnetic material used for the core or the magnetic circuit. So today I have this very basic but very important and relevant numerical example. Today we are dealing with something that is close to the real life characteristic of the materials. Today we are using the real BH curve that is basically the relationship between the magnetic field strength and the magnetic field density. So to show you how to use those curves, well, today we are having this very interesting and exciting example. So without further delay, let's start by reading this statement over here. The electromagnetic on the figure Q1A has a cast iron and steel section. So in other words, this configuration over here on the left-hand side received the name electromagnet. We have here a winding, and in this winding there is electric current that is moving around. So when this current is moving through this conductor, well, we have a magnetic flux density, and there are magnetic flux moving in those two sections of material. On the top, we have a section that is like a Z, and that is for the sheet steel. And in the bottom here, we have another section that is like a rectangle, and that section is basically cast iron. Well, the good news is that the cross section in both material, the cross section here and the cross section there, both cross sections, they have the same size, and you can see over here 6.4 square centimeters. Here there is a magnetic flux, and this magnetic flux is given here. You can see 3.5 exponent minus 4 Weber, and we know the whole description of the lengths for the different sections. To define the different sections, we use letters. You can see over here A, B, B, C, C, D, D, E, F. So basically, we have the whole geometrical definition of this configuration, and in general sense, we know the total length of both of them. What is very relevant for the example today is that we are using this BH curve. This received the name BH curve because, as you can see over here, there is a vertical axis that is representing the magnetic flux density, and in this case the unit for this case is Tesla. On the horizontal axis we have here the magnetic field strength using the letter H, and the units over here are amps turn per meter. So in figure Q1B you can see that I have the full range of magnetic flux strength starting from 0 and going up to 4,500 amps turn per meter. However, you must realize that there is here a red rectangle, and this red rectangle, what it's doing is basically creating a zoom of this section at the very beginning from 0 to 700. You can see that over here we have one section that is starting from 0 to 700, and that is this section over here. And on the vertical axis, you can see that it's going from 0 to 1.4. So basically what I am trying to explain here is that this figure 1C is basically, this figure Q1Z is basically a sum of this section over here, okay? So today we are using two material. The section on the top is steel, the section at the bottom is iron. It's not a traditional configuration. However, we are using here two different material to show you how to use those BH curve, okay? So over here, you can see that we have three questions. And the question A is determine the magnetic flux density B, in this case Teslas, for each section. We have two sections, steel and iron. So you can see the numerical result over there. Then we have question B, determine the magnetic field strength or magnetic field intensity, and the letter is H. And in this case, we have again two sections, one for the iron, one for the steel. And you can see over here the numerical results and the units per turn over meter. Finally, and probably the most exciting question is, what is the current, electrical current I in amps that we need in this electromagnet in order to establish the already indicated flux of 3.5 exponent minus 4 Weber. And you can see over there the answer, okay? So without further delay, let's start to solve or start the resolution of this very exciting numerical example. So the first step over here is we need to obtain the magnetic flux intensity. The magnetic flux intensity is relevant and important in this problem because the magnetic flux density B will be the input, the main input to solve this problem. In this example, we have two sections, so we will have a B for the sheet steel and one for the cast iron. You remember here the equation, the magnetic flux intensity, density is the magnetic flux divided by the cross-section area. And as you can see, after we put the number together, you can see on the top the magnetic flux that is identical for the two magnetic sections, the two different materials. And the reason is because we are using a series magnetic circuit. So the flux is the same, the cross section is the same because the geometry. So as expected, the flux density B is identical in both material, and you can see that is numerically equal to 0.5425 Teslas, okay? In summary, again, we have the same flux that is moving for two different materials. The material has the same cross-section, so it's expected that the magnetic flux density will be the same. So now, with this magnetic flux density, what we want to do is to obtain the magnetic flux intensity H. So in order to obtain the magnetic flux intensity H, we will use those magnetic curves that I already defined, the BH curve, and for that we will use a very simple method that is called the graphical method. The graphical method is extremely simple because what we need to do here is, well, we have one input over here, and that is the magnetic flux density that we calculate, 0.5 Teslas. So we draw here a horizontal line and it's intersecting the two different materials. So first, for the iron, it's very simple to see that the intersection is happening here at the point 2. So then we plot a horizontal axis a horizontal line, parallel to the horizontal axis. And here we obtain the magnetic intensity in the iron. Here the number is 1600. We understand that when you are using the magnetic flux intensity in this graph, you have the issue that this is basically a plot. So you can have some, I will say, deviation on your results because the appreciation of the horizontal and vertical axis. However, for this exercise, we are totally sure that the correct numerical answer is 1600 ampere turn per meter, because we use the real data coming from the cast iron BH curve. So now we will repeat the graphical method for the other material. As you can see over here, for the other material, that is the steel, you can see that it's very difficult to see the value on the horizontal axis, and that is the reason that we are using the second graph, the second plot, Q1C, because the Q1C is basically a sum of the whole curve. And again, what we are doing is, starting here from the input, we plot a horizontal axis, we intersect here on the point 2, and then we use this vertical straight line, and we obtain very simple, we obtain over there the magnetic intensity of the material, in this case is the steel, and you can see the number that is around 7 amps per turn per meter. So we answered the question B, because here you can see that I wrote both solution, the solution for the cast iron, 1600 ampere turn per meter, and over here we have the steel material, and you can see that is only 70. So in this case, we can say that with less current, we can establish the same magnetic field strength. So in conclusion, we can clearly say that the steel material is much better from the magnetic point of view for this electromagnet, okay? Now, what we need to consider is the geometry. So in the geometry, as you can see over here, we have the data, the distance, the length for every single point that we define here. We have A, B, B, C, C, D, D, E, E, F. So what we want to do now is to calculate the total length of the cast iron section, and that is B, C, D, E, and the total length of the steel sheet. In this case, the material is defined between the points E, F, A, B. So it's question just to use the lengths, individual lengths, and we obtain over here, this will be the length for the cast iron, 1.27 exponent minus 3 meters. And over here you can see the length, total length for the steel section, and in this case is 30.4 centimeters or 304 exponent minus 3 meters, okay? So beautiful. Now we have the total length of each section, and this information is extremely relevant because we want to obtain the current that is moving in this magnetic in this winding, and what we need to do is the following. You must remember that there is something called magnetomotive force, and the magnetomotive force is related or connected to the current and the number of turns. But also, you must remember the definition of the magnetic field strength, and that is the MMF, divided by the total length. So what I am doing now is substituting here the definition of the MMF. And as you can see over here, I can calculate the current as the over here as the H multiplied by L divided by the total number of turns, okay? In other words, what I am telling you is that we can obtain over here the current as the division between the MMF and the number of turns, but now the MMF is H multiplied by L. So we are using this approach, and now what we will do is remember that this is a magnetic circuit. This is a series magnetic circuit. And in this series magnetic circuit, we have two different materials. So when the magnetic flux is moving, there is MMF here across the steel and also across the iron. And that flux is created by this winding over here. So what we can do is to calculate the MMF across the steel and across the iron, because we know that for the steel, 7 amps turn per meter is the magnetic intensity for the steel, and then we multiply by the total length, and we are obtaining the MMF in the steel sheet and also in the iron. In other words, we know the MMF here, we know the MMF here, but we don't know the MMF here. So what we need to do is basically this is a series magnetic circuit, and in this series magnetic circuit I can use what is called the Ampere circuital law, that is equivalent to the Kirchhoff voltage law. In other words, this MMF is equal to the MMF here plus the MMF here. So the total MMF created by this winding should be the MMF drop here and there. In other words, the MMF on the iron and the steel. And when we combine those values that we already obtained, well, we know that in order that this magnetic circuit works, we need an MMF in the winding over here of 223 amps per turn. So finally, what we need to do is divide this 223.2 amp per turn by the total number of turns in the winding, and from there, dividing those two numbers, we obtain the current, and in this case is 3.7209 amps. So this is a very interesting, very exciting example. And in this example, what is very, very important for you is that we are using an electromagnet with two different materials. And those materials, the magnetic properties are defined by this BH relationship. So in this example, we use magnetic circuit theory. We use the BH curve, that is basically the fundamental relationship for the magnetic characteristic of the material. And with that, we were able to calculate the current in this electromagnet. So this example is very quite useful because you will learn basics and understand the concepts, but also close to the reality because you are using the proper BH characteristic of the material. Well, I am afraid that we are reaching the end of this video. I hope you enjoyed this video. If yes, please subscribe to the YouTube channel in order that you will be informed about the new videos. But also, if you have any question, any comment, or any suggestion for improving the videos or the channel, please feel free to drop an email, or simply you can just add a comment here, and I will be extremely helpful to help you. Thank you very much for watching, and I will see you at the next one. Bye now.